Hi, so today we're going to look at differentiation by first principles. So our learning intention is the knowledge of differentiation by first principles, and we'll be successful if we can differentiate or calculate f of x, f dash x, by applying this principle and recall the difference quotient and understand the difference of instantaneous rate of change and the average rate of change. Okay, all right. Let's imagine we have the parabola y equals x squared. If I have a point x equals 2, well then that y coordinate will be 4, because we're just squaring it, yeah? So that point here is going to be 2, 4. If I wanted to find a tangent at that point, or the rate of change at that point, one way is to find another point on the parabola and basically make a line and get the gradient of that line. So if I chose Q, which is basically the x equals 1, well the y value of that would be 1 as well using this formula. So if I was to plug that in, the gradient from P to Q at this moment is 3. If I was to move this point closer, so for example if I chose 1.9, so that's somewhere just a little bit closer, maybe there, and I was to draw those two lines, draw that point together, the rate of change has obviously slightly changed, but it's getting closer to the rate of change or the gradient at that point, yeah? Because when we take these 2 points, we're finding the average rate of change. So if I wanted to find the average rate of change between my point of P, which is 2, 4, and this new point R, which is 1.9, 3.61, I now get 3.9, a better estimation than my original estimation, because I was a bit far out here, but I'm getting closer and closer. I'm getting closer to the real rate of change. This is still the average rate of change because I'm averaging the 2 points. If I get really, really close, and I get to a point S, all right, so that's going to be 1.999, which is 3.996001, so close to P being 2. Right? If I found that gradient there, I end up getting to 3.99999, right? Which is getting so close to the instantaneous rate of change at that point. Obviously, with the 2 points, we're still averaging it out, but we're getting close to the instantaneous rate of change. Okay. This whole idea is that we approach the point and taking the averages, we're becoming close to the instantaneous rate of change, and that is the whole point of the differentiation by first principles. If we can calculate the derivative of a function by having the limit as the step getting closer and closer to nothing over the function, and that's the average rate of change. Let's do some examples. Okay, let us say that we have a function y equals x squared. Okay, if we're going to differentiate by first principle, f of x is the limit as h approaches 0 of x plus h minus the original function over the step size of h. So let us work that out. Okay, so I want the function of x plus h. So every time I see x in my original function, what I'm going to do is going to write x plus h. There's the square, so to keep that, I'm going to minus the original function, which is x squared, and that's going to be over h. All right. If I was to expand this top part out, so it'll give me x squared. X times h is xh, and double that is 2xh plus h squared, and then minus x squared. all over h. Well, this cancels out this, leaving me 2xh plus h squared all over h. Now, if I cancel it out, I get 2x plus h. Now, when h gets to 0, I get just 2x. So f dash of x is 2x. Okay, let's try this one. Okay, so using the formula, f dash x is the limit as h approaches 0 of fx plus h minus f of x all over h. Okay, so x plus h, every time I see an x in my original function, I have to write x plus h. That's the squared. And now I'm going to have to write x plus h again. Alright, that is that part. I'm going to minus the original function, and that's the original function. And that's all over h. Let's expand the top. We get x squared plus 2xh plus h squared plus x plus h minus x squared plus x all over h. Let's collect like terms. So that will cancel this. This cancels that part. So we get 2xh plus h squared plus h all over h. If we cancel that out, we end up getting 2x plus h. As h approaches 0, we still get 2x. That cancels out. That's a h. Yep. Oh, h by h is just 1. Sorry. Yep. And as h approaches 0, it just leaves us 2x plus 1. Okay. Alright, so if we want to find the instantaneous rate, we actually, when x equals 2, we do want to find when f dash is 2. So when we multiply that 2 into there, we get instantaneous rate is 4. And that's very, that is what we found by doing the difference quotient. Okay, if we wanted to find out this one, we plug in 2, so we get 5, and that's the instantaneous rate at that point for this function. Okay, thank you very much.